For the exciting conclusion to the forces chapter, we're going to figure out how fast someone would be going if they skied down an incline of 25 degrees over a distance of 150 meters. I'm curious about this because I did this one morning on the ski slopes in Vermont. I went to the highest, steepest, coldest slope where if the ice is colder, it kind of slides better. There's a lower coefficient of kinetic friction between your skis and the snow. And I had waxed my skis up that morning to make the coefficient of kinetic friction even lower. So it was like 5 degrees, and the slopes had just been groomed, so they were perfectly flat and very, very slippery for not a lot of resistant force from friction. And I got going real fast by the time I got to the end. So here's how, neglecting air resistance, here's how one could figure out how fast I was going. And this is a kind of dynamic problem, so it incorporates skills from the previous chapters. But let's just focus on the skills from this chapter. The first thing we have to do is find my acceleration. And if we're ignoring air resistance, then that acceleration is going to be constant the whole time because the gravitational force is constant the whole time. But here's the trick to this problem. Gravity always acts straight vertically downward, but the acceleration due to gravity is only parallel to the slope that you're on. So this is a situation where we have to decompose the force of gravity vector to find its component parallel to this 25-degree slope. There's me. Don't make fun of my drawing. And here's gravity acting on me. This is my mass m. This is the acceleration of gravity, 9.8 meters per second squared. And here's the trick here. Here's a case where you actually want to rotate your coordinate system. So your x-axis, let's say our x-axis is actually parallel to the slope. And our y-axis is perpendicular to the slope. And we can recognize that we're actually on a pretty flat slope. This slope is really more flat than it is sloped. It's not quite, it's about halfway to 45 degrees. So the component of the force of gravity that acts along the slope is going to be less than half of the magnitude of my weight of the mg vector. So we'd expect that to be pretty short. And then the component of mg along the y-axis would be almost the full length of that vector, of that the mg vector. So here's our rectangle. So the short side is the one going parallel to the slope. And the next step is to figure out where theta is. Where's our 25 degrees? And if we look at this and think about it for a second, we can figure out that this smaller angle here is 25 degrees. Or also this angle here, we could look at it like that. And when we look at it that way, we see that this is the side length of a triangle we want to find. Here's the triangle. We want to find this side length here, and we can use a trigonometric identity. SOHCAHTOA. Let's see, this side is opposite to 25 degrees, so we can use sine. And we know that sine 25 is the opposite side over the hypotenuse, and here the hypotenuse is mg. That is the vector that is the longest side of this triangle. And when we rearrange that equation, we get an expression for that opposite side length, which is this vector, this force vector that's accelerating me down the hill. So we can go ahead and label that vector mg sine 25. But that is not the only force acting on me, oh no. There's also the force of friction, because there is some friction between my skis and the snow, and that is acting in that direction. It's opposing the motion. So that's Ff, force of friction. So we need to figure out what that is so we can find the sum of all forces on me. The net force on me in the x component, let's call this the net force along the x-axis would be the force of gravity parallel to the slope minus the force of friction. And we do want to figure out what that force of friction is, and we have an expression for that. And we know the definition of the force of friction, of kinetic friction, is the normal force times the coefficient of kinetic friction. And we're given a coefficient of kinetic friction, we have to find the normal force. And an important thing to understand here is the normal force is always perpendicular to the ground. So here the ground is at a 25-degree angle. The normal force is going to act up perpendicular to the ground. And here's the thing. While I'm skiing down the slope, I'm not accelerating off the slope. I'm not like going into the air, and I'm not accelerating into the ground either. What I'm trying to get at here is my acceleration along the y-axis is 0. So therefore, the sum of all forces along the y-axis on me is also 0. So, simply put, what I'm trying to get at is that the size of this normal force vector must be equal in magnitude but opposite to this vector here. And remember, this is the component of the force of gravity that acts perpendicular to the ground. And to figure out what this vector is, we can look at this triangle here. And we know that this angle is 25 degrees. We know that the hypotenuse is mg. And we're trying to find the side that is adjacent to the 25-degree angle. So we can use cosine. So we just take the hypotenuse and multiply it by cosine of 25 degrees to find the y component of the force of gravity vector, which we have concluded must be equal to the normal force. So I just labeled these vectors here, mg cosine 25 for this one, and then the normal force, which is equal and opposite to that mg cosine 25. And what we can do now is insert that definition of the normal force into here and put in our value of 0.1 for the coefficient of kinetic friction. So we finally have an expression for the net force along the x-axis on me, and that is the force this is the force responsible for accelerating me down the slope. And this whole chapter is about sum of forces equals mass times acceleration. So we can use this equation to find that acceleration. So I'm just going to insert my mass times my acceleration in place of the sum of all forces here. And now here's the payoff. And we can simplify this equation here greatly by canceling all the m's. And this is a great example of why you should wait to put in numbers for variables until you've actually solved for the variable you want to solve for. Because we could have stressed out about how much do I weigh, let's put in a number for my mass. But we don't have to do that because there's an m in every term in this equation, so we can just make those disappear. So what we essentially did with that step is just divide both sides by m to make the m's go away. So now we just need to insert 9.8 for the g's and then run this through our calculator. And that should be our answer for the acceleration. And you've probably forgotten what we were actually trying to solve for by now, which is the speed at the bottom. But this is pretty impressive to get this far and get this value for the acceleration. Now it just becomes a problem where we have to use a kinematic equation. Here's what we know. We just solved the acceleration, and we know we're going to travel a displacement of 150 meters, and we're trying to find the final velocity. So given all these variables, we can hopefully identify a kinematic equation that will allow us to solve for the VF, the final velocity. Oops. And that's it. So to solve for VF is just a one-step process. We're going to take the square root of both sides and then put in our numbers and plug those numbers in the calculator and get our answer. And that is more than 60 miles an hour. But there would have been some wind slowing the skier down. So probably in real life not quite that fast.